There is a star in the sky tonight that has been burning for longer than the earth has existed. You cannot see it with the naked eye. It is too far away, too dim, too ancient. But it is there, somewhere out in the dark between the constellations, fusing hydrogen into helium, releasing light, holding itself together against the relentless pull of its own gravity. It has been doing this since before our sun was born, before the solar system condensed from its cloud of gas and dust, before the first complex molecules drifted together in the primordial ocean of a young Earth. Before any of that, this star was already old, and one day it will go out, not with a bang, not with a supernova, not with the spectacular violence that ends the lives of the universe's most massive stars. This particular star will simply cool. It will exhaust the last of its fuel. It will shrink. It will fade from white to yellow to orange to the deepest red imaginable, and then below red into infrared, into frequencies our eyes cannot detect at all. And then it will be dark, cold, a cinder drifting through a universe that has long since moved on. The question that should keep you awake at night, the question that cuts through everything we think we know about forever, is this: when does the last one go out? Not this star, not our sun, not any individual star we've catalogued in any telescope. The last one, the final star, the one whose extinction marks the end of the stelliferous era, the age of stars, and plunges the universe into a darkness that will never, not once, not in any meaningful sense, lift again. We know the answer. Or rather, we know an estimate, and the estimate is so staggering, so incomprehensible, so far beyond anything human intuition can hold, that even knowing it doesn't quite feel like knowing it. It feels more like standing at the edge of a canyon at night and shining a flashlight into the dark. You see the beam reach out, you watch it dissolve into nothing, and you understand abstractly that the bottom is somewhere down there. But you cannot see it, you cannot feel it, you cannot reach it. That's what we're going to do in this video. We're going to shine the light, we're going to walk step by step, phase by phase, countdown, stage by countdown stage, from where we are right now, tonight, in this moment, all the way to the moment the last star in the universe burns out. It's going to take a while. The universe is approximately 13.8 billion years old. Say that number to yourself. 13.8 billion years. Let it sit there for a moment. It already sounds impossible. Most people cannot intuitively grasp 1,000,000 years, 100,000 generations of human beings, a span of time that dwarfs all of recorded civilization by a factor of 10,000. A billion is 1,000 millions. And we're talking about 13 of those billions plus most of another one on top. The Earth is 4.5 billion years old. The Sun is about 4.6 billion years old, which means that roughly 2/3 of the universe's history had already passed before our Sun even ignited. That's the context. That's the frame. We are not early in this story. We are, depending on how you measure it, somewhere in the middle, or perhaps toward the end of the beginning. But here is the thing that changes everything, the thing that reshapes how you understand the timeline we're about to walk through. The stars we can see right now, tonight, burning bright in the sky, the visible ones, the familiar ones, the ones we've named and catalogued and told stories about for 10,000 years, those stars are almost entirely the wrong kind of star to be asking about when we talk about the last one. The stars we see are mostly large, mostly bright, mostly hot, and large, bright, hot stars burn fast. Betelgeuse, that reddish-orange star in Orion's shoulder, the one that made headlines a few years ago when astronomers thought it might be about to explode. Betelgeuse is about 800 times the diameter of our Sun. It is so enormous that if you placed it at the center of our solar system, its surface would extend past the orbit of Jupiter. It burns through its fuel at a rate so prodigious, so wasteful, so cosmically irresponsible that it will exhaust its nuclear reserves in a cosmological eye blink. Betelgeuse is estimated to have somewhere between 100,000 and a few 100,000 years left before it goes supernova. 100,000 years. That sounds like a long time in human terms, but in the lifetime of a star, it is nothing. It is a rounding error. It is the last few seconds of a candle burning down after you've left the room. Rigel, the brilliant blue-white star at Orion's knee, is even more extreme. It burns at temperatures exceeding 20,000 degrees Kelvin at its surface, roughly 3.5 times hotter than our own Sun, and it is perhaps 120,000 times more luminous. Rigel is, in the truest sense, burning the candle at both ends. Its entire stellar lifespan will amount to something in the range of 8 to 10 million years. In cosmic terms, Rigel is a mayfly. Our own Sun, by contrast, has a total lifespan of around 10 billion years. It's currently about 4.6 billion years through that lifespan, which puts it roughly in the middle of its main sequence, the stable, hydrogen-fusing phase that we think of as a star's adult life. In another 5 billion years or so, it will exhaust its core hydrogen, swell into a red giant, potentially engulfing the inner planets, and then shed its outer layers as a planetary nebula before settling into a dim, cooling white dwarf. 10 billion years, 5 billion left. That feels like forever from where we're standing, but the star we're really interested in, the star whose death defines the end of the stelliferous era, is not Betelgeuse. It's not Rigel. It's not even our Sun. It is a type of star so small, so dim, so staggeringly numerous and overlooked that most people don't even know they dominate the galaxy. We're talking about red dwarfs. Red dwarfs are the most common stars in the universe. That sentence deserves to be read twice because it runs contrary to everything our nighttime intuitions tell us. When you look up at the sky, you see brilliant points of light. You see Sirius blazing in the winter sky. Don't you see Vega and Deneb and Altair forming the summer triangle? You see the blue-white intensity of hot, young stars, the orange-red glow of giant stars nearing the end of their lives, the steady, yellow-white burn of sun-like stars. The sky, from where we stand, looks populated by a dazzling variety of stellar objects, most of them at least somewhat comparable to our own Sun. But the sky is not a fair sample. The stars we see with the naked eye are overwhelmingly the bright ones. And the bright ones are not the typical ones. They are the exceptions, the giant, the luminous, the freakishly energetic. We see them because they're visible from Earth, not because they're representative of the galactic population as a whole. If you could somehow take a census of every star in the Milky Way, all 200 to 400 billion of them, you would find that somewhere between 70 and 80% of them are red dwarfs. 3 out of every 4 stars in our galaxy, roughly speaking, is a red dwarf. The universe is, in the most literal sense, dominated by these small, dim, slow-burning stellar objects that human beings didn't even know existed in their true numbers until we built telescopes sensitive enough to detect them. Red dwarfs, also called M-type stars or M dwarfs, are small. The smallest of them have masses as little as 7.5% of our Sun's mass, barely above the threshold required to sustain hydrogen fusion at all. Most range from about 10 to 50% of the Sun's mass. They are cool, at least by stellar standards, and with surface temperatures ranging from about 2,000 to 4,000 degrees Kelvin compared to our Sun's 5,778 degrees. They shine with a deep red or orange-red light, and they are dim, incredibly dim. Proxima Centauri, the nearest star to our Sun and a red dwarf, is only about 0.0017 times as luminous as the Sun. If you replaced the Sun with Proxima Centauri, Earth would become an ice world within months. The light reaching us would be dimmer than our current twilight. But here is the thing about red dwarfs that makes them central to the story of the last star in the universe. They burn slowly, almost unimaginably slowly. The physics works like this. A star's lifespan is determined by how much fuel it has and how fast it burns through it. A more massive star has more fuel, yes, but it also burns it far faster. The relationship is not linear, it is exponential. A star twice as massive as the Sun doesn't live twice as long. It lives roughly 8 times less long because the increased pressure and temperature in its core drives fusion at a dramatically accelerated rate. This is why the universe's most massive stars, those 20, 50, 100 times the mass of the Sun, live only a few million years. Red dwarfs invert this relationship in the most extreme way possible. They have much less fuel than our Sun, but they burn it at such a glacial, unhurried pace that their lifespans don't just exceed our Sun's, they exceed it by orders of magnitude. The estimated lifespan of a mid-sized red dwarf, say one with about 20% of the Sun's mass, Claire, is approximately 1 to 2 trillion years. Trillion, with a T, our Sun's lifespan is about 10 billion years. 1 trillion years is 100 times longer than that. The universe itself is currently 13.8 billion years old. A trillion years is roughly 72 times the current age of the universe, and that's a mid-sized red dwarf. The smallest red dwarfs, those barely massive enough to fuse hydrogen at all, have theoretical lifespans approaching 10 trillion years. Some estimates stretch to 12 or even 15 trillion years for the most minimal stellar objects that still technically qualify as stars. This is the number we're counting down to. This is the deadline baked into the structure of the cosmos itself. Somewhere between 1 trillion and 10 trillion years from now, the last red dwarf in the universe will exhaust its fuel supply and fade from a dying ember to a cold, dark cinder. The age of stars will end. And everything, every planetary system, every possible orbit around a stellar fire, every source of heat and light in the cosmos will go dark. But we're getting ahead of ourselves, because before we reach that final moment, before we count down to the death of the last red dwarf, we need to understand what happens on the way there. What does the universe look like as it loses its stars one by one? What phases does it pass through? What changes? What disappears? Because the death of the last star is not just a single event at the end of a very long timeline. It is the culmination of a process that is already underway. The countdown, in a very real sense, has already begun. Let's start where we are. Right now, in the present era, the universe is in what cosmologists call the stelliferous era, from the Latin stella, meaning star, the age of stars. This is the epoch we inhabit, a universe lit by nuclear fires warmed by stellar radiation, populated by planetary systems gathering heat and light from nearby suns. By cosmic coincidence or cosmic inevitability, depending on your philosophical inclinations, this is also the era in which life as we know it became possible. Because life as we know it requires energy gradients, requires warmth, requires the kind of stable, long-lasting, reliable energy output that only a middle-aged star on the main sequence can provide. The stelliferous era began shortly after the Big Bang, roughly 100 million years after, when the first stars ignited in the primordial dark. It will end, in the rough estimation of modern cosmology, somewhere around 100 trillion years from now, when the last red dwarf finally exhausts its fuel. We are 13.8 billion years into an era that lasts 100 trillion years. To put that in terms your brain might find slightly more graspable. If the stelliferous era were compressed into a single calendar year, all 100 trillion years of it compressed into 365 days, then the current moment, 13.8 billion years in, would represent approximately the first 18 hours of January 1st. We are not even close to the middle. We are in the opening minutes of a story that hasn't yet found its stride. But the universe, even now, in this opening chapter, is already changing. It is not static. The stellar population is not the same as it was a billion years ago, and it will not be the same a billion years from now. The rate of star formation in the universe has been declining for roughly the last 11 billion years. This is one of the most important and underappreciated facts in all of cosmology. Star formation, the process by which giant clouds of gas and dust collapse under gravity, heat up, and ignite fusion, requires raw material. It requires hydrogen. It requires the diffuse molecular clouds that fill the space between existing stars, waiting for some perturbation. A nearby supernova, a galactic collision, a gravitational instability to trigger their collapse. The universe started with an enormous supply of this raw material. In the era right after the Big Bang, hydrogen and helium filled the cosmos in vast quantities, and the first stars formed in prodigious abundance. But each generation of stars locks up some of that hydrogen inside stellar cores, fuses it into heavier elements, and then, at the end of the star's life, either ejects those heavier elements back into space, in the case of smaller stars, or collapses into a remnant that retains much of its mass forever, in the case of larger stars and neutron stars and black holes. Over time, the universe's supply of raw star-forming material depletes. The hydrogen gets used up, locked up, or dispersed into forms that can no longer easily collapse into new stars. And so the rate of new star formation falls. Studies of galaxy surveys and cosmic star formation rates suggest that the peak era of star formation in the universe occurred roughly 10 billion years ago, about 3 to 4 billion years after the Big Bang. This was the universe's most productive epoch for creating new stellar objects. Galaxies were forming, colliding, merging, gas was abundant. The conditions for stellar ignition were nearly ideal. Since then, the rate has been falling. It has been falling for 10 billion years. It is falling right now, tonight, as you listen to this. Every decade that passes, slightly fewer new stars ignite than ignited in the decade before. The universe is winding down its stellar production slowly but relentlessly, like a factory reducing output, not because of a single decision, but because the raw materials are running thin. Current estimates suggest that the universe today is forming new stars at only about 3% of the peak rate it achieved 10 billion years ago. 3%. Our galaxy, the Milky Way, forms somewhere between 1 and 3 new stars per year at current rates. That sounds like a lot until you realize that in the universe's peak star-forming epoch, our galaxy's predecessor structures were forming hundreds of times more. The slowdown is not catastrophic on any human timescale. It is not even dramatic on any timescale a civilization might easily perceive. But it is real, it is measurable, and it points in only one direction. So here is the first phase of our countdown, not a countdown to a single event, but a countdown through stages, each one longer than the last, each one darker and quieter and emptier than the one before. The first phase, the death of the giants. Right now, as we speak, the universe's most massive stars are already dying. They were born recently, in cosmic terms, millions or tens of millions of years ago, in the same era as our solar system in rough magnitude terms, and they are burning through their fuel with reckless, extravagant speed. The O-type stars. And the most massive stars in the universe live for only 1 to 3 million years. They are the bright blue blazes of stellar youth, ferociously hot, ferociously luminous, ferociously brief. Many of the blue-white stars you can see with the naked eye tonight are O-type or B-type stars. They look eternal from our perspective. They are, cosmologically speaking, the light of dying embers already. Over the next few tens of millions of years, a span of time our galaxy will traverse without meaningful change, a period during which the Milky Way will complete not even a single rotation around its center. These massive stars will burn out. The ones that haven't already exploded as supernovae will do so. Each one will leave behind either a neutron star, a city-sized ball of matter so dense that a teaspoon of it would weigh 1 billion tons, or a black hole. When the last O-type star explodes, sometime in the next few tens of millions of years, the universe will lose its hottest, brightest, most energetic stellar objects. The brilliant blue-white fires will be gone. What remains will still be plentiful, billions upon billions of stars, but the color palette of the cosmos will shift slowly and imperceptibly from any single vantage point toward yellow, then orange, then red. This is already happening. The second phase overlaps the first, the slow attrition of sun-like stars. Our sun is a G-type star, a yellow dwarf, though its light is actually white when seen from space. G-type stars have lifespans of roughly 10 billion years. Our Sun has about 5 billion years left. The Sun-like stars born around the same time as our Sun, in the same galactic epoch, in roughly similar conditions, are all on approximately the same schedule. In the next 5 to 7 billion years, this entire cohort of Sun-like stars will exit the main sequence. They won't go quietly. As a G-type star exhausts its core hydrogen, it expands into a red giant, brightening as it swells, in the Sun's case, ultimately expanding to perhaps 200 times its current diameter, potentially absorbing Mercury and Venus and roasting Earth to a lifeless, ocean-free rock in the process. Then, over the following billion years or so, it sheds its outer layers in a spectacular expanding shell of gas called a planetary nebula, and the remaining core, an object about the size of Earth but with half the mass of the original star, settles into its final form, a white dwarf. White dwarfs do not fuse hydrogen. They are not stars in the active sense. They are the cooling corpses of stars, remnants that emit heat and light only because they are still hot from their former nuclear activity. Over trillions of years, a white dwarf will cool from white to yellow to orange to red to the deepest infrared, and eventually it will become what physicists call a black dwarf, a cold, dark object at near absolute zero temperature, invisible and inert. But this cooling takes an extraordinarily long time. The universe is currently not old enough for any white dwarf to have cooled to the black dwarf stage. The white dwarfs in the universe today are still warm, even still glowing faintly. The oldest ones are perhaps 10 to 13 billion years old and have cooled to temperatures still detectable by sensitive instruments. True black dwarfs, the final graveyard markers of sun-like stellar evolution, won't exist in meaningful numbers for many trillions of years. For now, they are a future state, an endpoint on a cooling curve, a destiny not yet reached. Let's hold the frame here, at the current moment, and establish what we're counting down from. The universe right now contains, by most estimates, somewhere between 100 billion trillion and 200 billion trillion stars. That's written as 10 to the 23rd power to 2 times 10 to the 23rd power. 200 sextillion stars. It is a number so large it defies any intuitive comparison. If you counted 1 star per second, it would take you 3 trillion years just to count them all. Of those stars, the vast majority, roughly 70 to 80%, are red dwarfs, and they will still be burning when our sun is long dead, when all the sun-like stars in the galaxy have gone through their red giant phase, shed their planetary nebulae, and cooled toward white and then dark dwarfs. This is the remaining population when the real countdown begins. Not the bright, familiar stars, not the ones we see tonight, the ones we can barely detect, even with modern telescopes. The ones that have been quietly burning unnoticed and uncelebrated since the early universe. The ones that will still be burning when everything we consider stellar civilization, every star with a habitable zone, every sun that could warm a planet to liquid water temperatures, has already died. The red dwarfs. And here is the thing about red dwarfs that makes them both the last survivors and, in a strange way, the most hopeful objects in the universe. Some of them might have planets. Some of those planets, despite the challenges, the intense flares these stars produce in their youth, the tidal locking that keeps one face always toward the star, might have conditions compatible with life. The last star in the universe will be a red dwarf, and it might have worlds. Whether those worlds will be inhabited when it finally dims and dies, whether there will be something in the universe capable of watching the last light go out, is a question we cannot answer. But it is the question that pulses beneath everything we're going to talk about in this video. The countdown is not just a timeline of physics, it is a timeline of possibility, of whether there will be anyone left to count. Let's talk about what the galaxy looks like right now that sets the clock for everything ahead. The Milky Way contains something in the range of 200 to 400 billion stars. Of those, perhaps 150 to 300 billion are red dwarfs. Our nearest stellar neighbour, Proxima Centauri, just 4.24 light-years away, is one of them. It is a red dwarf with a mass about 12% of the Sun's and a luminosity less than 0.2% of the Sun's. It has at least one confirmed planet in its habitable zone, a world called Proxima b. Whether that world is actually habitable is hotly debated. Proxima Centauri is a flare star, prone to violent ultraviolet and X-ray outbursts that could strip away an unshielded atmosphere in relatively short order. But Proxima Centauri will still be burning hydrogen long after our Sun has expanded into a red giant and scorched every living thing from the surface of Earth. Proxima Centauri's estimated lifespan is approximately 4 trillion years. It is currently less than 5 billion years old. It has not yet reached middle age. Now consider that Proxima Centauri is not unusual among red dwarfs. It is not the smallest. It is not the most long-lived. There are red dwarfs in the Milky Way even less massive, even dimmer, even more fuel-efficient. TRAPPIST-1, the famous red dwarf that hosts a system of 7 rocky planets, 3 of which orbit in or near the habitable zone, has an estimated lifespan of around 12 trillion years. It is currently less than 8 billion years old. It is, in cosmic terms, an infant. TRAPPIST-1 will still be fusing hydrogen long after the universe has aged by a factor of nearly 1,000 compared to its current age. These stars, Proxima Centauri, TRAPPIST-1, and hundreds of billions of their siblings throughout the galaxy, are the main characters of the story we're telling. They are the long-burning candles of the cosmos, and their eventual extinction is what defines the end of the age of stars. The countdown, in the most precise sense we can give it, goes something like this. In 5 billion years, our Sun will leave the main sequence. In 10 billion years, most Sun-like stars will be cooling white dwarfs. In 1 trillion years, the most massive red dwarfs will begin to exhaust their fuel. In 10 trillion years, the last red dwarfs will be entering their final phases. Somewhere between 1 and 100 trillion years from now, and most estimates center around 10 trillion years, the last star in the universe will go out. That's the timeline. But a timeline is not a story. A story needs texture. It needs the details of what happens at each phase. It needs to answer the question that sits under every number in that list. What does the universe actually look like as this is happening? What has been lost? What survives? Is there anything left that could call itself awareness or civilization or life? That's what we're going to spend the rest of this video exploring, because the death of the last star is not just a number on a scale. It is the culmination of a process that transforms the universe from the place we know, warm, lit, busy with the business of stellar and planetary life, into something so alien, so cold, so dark and empty that calling it the same universe might be the greatest act of semantic generosity in the history of description. But before we get there, before we walk through the intermediate stages, before we watch the universe dim and cool and go quiet, we need to understand one more thing about where we are right now. We need to understand that the countdown doesn't just describe what's going to happen to the stars. It describes what's going to happen to everything that depends on them, including, if they survive long enough, us. 5 billion years is not a long time. Not in the context of the story we're telling, not measured against a countdown that runs to 10 trillion. 5 billion years on the timeline we're walking is barely a step. It is less than 0.1% of the total span between now and the death of the last star. It is a rounding error on a cosmological scale, and yet 5 billion years is the number that matters most to us, because 5 billion years from now, give or take a few 100 million, our Sun will leave the main sequence. It will begin its transformation from the stable, middle-aged, hydrogen-fusing star that has sustained every living thing that has ever existed on this planet into something unrecognizable, something deadly, something final, at least for Earth. The death of our sun is not the death of the last star. It is not even close, but it is the death of our star. And understanding what happens to our sun, and why and what the solar system looks like in the aftermath, gives us the template for understanding what happens to every other sun-like star in the universe over the next several billion years. The Milky Way contains somewhere between 50 and 100 billion G, K, and F-type stars, stars comparable to our Sun in mass and lifespan. Our Sun's death is not a unique event, it is a preview of a wave that, over the next 10 billion years, will extinguish tens of billions of stellar fires across the galaxy, leaving behind a cooling graveyard of white dwarfs and stripped planetary systems. So let's start there. Let's start with the death of the familiar. The Sun is currently 4.6 billion years old. It sits at almost precisely the midpoint of its main sequence lifespan. Right now, in its core, hydrogen fusion is proceeding at a steady, yet reliable rate, roughly 620 million metric tons of hydrogen converted to helium every single second. That is not a typo. 620 million metric tons per second. And yet the Sun is so massive, so incomprehensibly large, containing 99.86% of all the mass in the solar system, that this profligate consumption barely puts a dent in its reserves. The Sun can sustain this rate of consumption for another 5 billion years. During this stable period, the long middle age of our star, not much will change perceptibly. The Sun will gradually brighten, as it has been doing since its birth. A slow, steady increase in luminosity, driven by the gradual accumulation of helium ash in the core, which forces the fusion reactions to move slightly outward and intensify. Over the next billion years, the Sun will be about 10% brighter than it is today. In 2 billion years, about 20% brighter. In 3 billion years, perhaps 30 to 40% brighter. This matters enormously for Earth. The habitable zone, the range of orbital distances where liquid water can exist on a planetary surface, is not fixed. It is defined by the star's luminosity, and as the Sun brightens, the habitable zone migrates outward. At some point, somewhere between 500 million and 1.5 billion years from now, depending on atmospheric feedbacks and geological processes, Earth will cross the inner edge of the habitable zone. The oceans will begin to warm, water vapor will accumulate in the upper atmosphere. More water vapor means more greenhouse warming. More greenhouse warming means more evaporation. The cycle accelerates. The oceans evaporate. The hydrogen from water vapor is gradually lost to space, stripped away by solar radiation, and Earth becomes a world without liquid water, a hot, desiccated rock, something resembling a hotter, drier version of Venus. This is the first deadline in the Sun's countdown, not the Sun's death. The Sun itself will still be burning, still fusing hydrogen, still shining. But life, as we understand it on Earth as we know it, will have become impossible somewhere in that 500 million to 1.5 billion year window. 500 million years. That is the number that should give you pause. Not 5 billion, 500 million. The geological record shows that complex multicellular life appeared on Earth roughly 600 million years ago. We are already 3/4 of the way through the window in which complex life is possible on this planet, measured against this particular solar constraint. The age of animals, the age of forests, the age of everything that walks or swims or flies, it all fits inside a window that is already most of the way closed. What happens after that is someone else's problem, or perhaps no one's problem. It depends entirely on what we do between now and then. But let's follow the sun forward past that point. The sun, indifferent to the fate of the world it warmed for 5 billion years, keeps burning. 5 billion years from now, the hydrogen in its core is depleted, not all at once. The transition is gradual, playing out over hundreds of millions of years, but the core hydrogen runs out. Fusion in the core stops. Gravity reasserts itself, compressing the core, heating it. The additional heat causes hydrogen in the shell surrounding the core, hydrogen that was previously too cool to fuse, to begin fusing. The shell burns. The energy output from this shell burning is larger than what the core produced during stable hydrogen fusion, and the added energy pushes the outer layers of the sun outward. The sun begins to expand. This is the beginning of the red giant phase, and the numbers involved are staggering. Over the following billion years or so, the sun will expand from its current diameter, roughly 1.4 million kilometers, to something on the order of 200 times that size. 200 times. The sun's radius will grow to approximately 200 solar radii, placing its surface somewhere around 0.9 to 1.0 astronomical units from the solar center. The Earth orbits at 1 astronomical unit. This means the sun, at peak red giant expansion, will have a surface that extends almost to Earth's current orbit. The precise outcome for Earth is debated. Some models suggest Earth will be engulfed, swallowed by the sun's expanding envelope. Others suggest that the sun's mass loss during the red giant phase, it will shed perhaps 30% of its total mass, will cause Earth's orbit to spiral slightly outward, potentially keeping it just outside the photosphere. Either way, any surface liquid water, any atmosphere, any remnant of whatever passed for civilization will be vaporized long before this point. At peak red giant luminosity, the sun will be thousands of times more luminous than it is today, and Earth's surface temperature will be measured in thousands of degrees. But there is something stranger and quieter that happens during the red giant phase, something often overlooked in the dramatic narrative of Earth's incineration. The outer solar system gets warmer. Mars, currently a frozen desert, would see its surface temperatures rise significantly as the red giant sun pours vastly more energy into the solar system. The ice on its poles would melt. Perhaps liquid water would pool in its ancient lowlands for a brief geological window. Further out, Europa and Enceladus, the ice-covered moons of Jupiter and Saturn that are currently considered among the best candidates for existing extraterrestrial life in our solar system, because they harbour subsurface oceans beneath their frozen crusts, would see their ice shells melt. The subsurface oceans, currently hidden under kilometers of ice, would be exposed to space, evaporating away. The habitable zone, which for the past 5 billion years has sat close to Earth's orbit, will sweep outward, past Mars, into the asteroid belt, out toward Jupiter and Saturn. For a brief window, perhaps a few 100 million years, the moons of the outer solar system will be warm. Not for long. Not long enough, perhaps, for life to begin from scratch if it hasn't already, but warm. Then the sun contracts again. After the red giant phase comes something astonishing. As the sun swells and cools and bloats at the tip of the red giant branch, the helium ash that has been accumulating in its core reaches a critical density and temperature, in what stellar physicists call the helium flash. The helium in the core ignites all at once. a runaway nuclear event that releases more energy in a few seconds than the Sun emits in millions of years, but which is entirely contained within the stellar interior and invisible from outside. In the aftermath, the Sun settles into a new stable configuration, smaller than its red giant size, fusing helium in its core and hydrogen in a surrounding shell. This phase, the horizontal branch or the helium-burning main sequence, lasts roughly 100 million years. The Sun burns helium into carbon and oxygen. From outside, it appears as a smaller, cooler, yellowish-orange star. Nothing dramatic, just a quieter ember. But helium is a finite resource too, and it runs out faster than hydrogen did. When the helium in the core exhausts, the process repeats in a more extreme version. The Sun expands again, this time into what's called an asymptotic giant branch star. Larger than before, more luminous, more unstable, and this is where the Sun begins to fall apart. On the asymptotic giant branch, the Sun becomes subject to thermal pulses, periodic explosions in the hydrogen and helium shells that drive enormous mass loss. The outer layers of the Sun, its envelope, are no longer gravitationally bound. They drift away in a slow stellar wind, expanding outward from the solar system in a shell of gas and dust. This expanding shell is what we, from a safe astronomical distance, would call a planetary nebula, a glowing cocoon of expelled stellar material illuminated by the hot, shrinking core at the center. The planetary nebula phase lasts maybe 10,000 to 30,000 years. In that brief time, the Sun's expelled envelope travels outward at speeds of tens of kilometers per second, eventually dispersing into the interstellar medium, seeding the galaxy with carbon, nitrogen, oxygen, the heavy elements forged in the Sun's core over billions of years of fusion. These atoms will drift in the galaxy for perhaps billions of years before being incorporated into the next generation of stars and planets. Our Sun will eventually become someone else's atoms. When the envelope is gone, what remains is the core, a dense, hot object about the size of Earth, containing roughly half the original mass of the Sun, with a surface temperature initially around 100,000 degrees Kelvin. It is too small to sustain fusion. It has no fuel left. It is simply hot from everything that came before. This is a white dwarf. White dwarfs are fascinating, eerie, and deeply important to the countdown we're tracking. A white dwarf is not a star in the active sense. It is not fusing anything. It has no energy source beyond the thermal energy stored in its crystalline or liquid interior. It glows simply because it is hot, and it will cool very slowly over an incomprehensible span of time. The Sun's white dwarf remnant will begin at a surface temperature of roughly 100,000 degrees. It will radiate heat away into space. Slowly, over billions of years, its surface temperature will drop to 80,000 degrees, to 50,000, to 20,000, to 10,000. The Milky Way's oldest white dwarfs, formed in the galaxy's earliest star-forming epochs roughly 13 billion years ago, have cooled to temperatures of around 3,500 to 4,000 degrees Kelvin, dimly red, barely visible. And they are still cooling. The cooling never stops. It just gets slower and slower as the temperature differential between the white dwarf and the surrounding space decreases. In perhaps a quadrillion years, 10 to the 15th power years, a number so large it makes our trillion-year red dwarf lifespans look modest, the Sun's white dwarf will have cooled to the temperature of the cosmic microwave background radiation. At that point, it will have reached thermal equilibrium with the universe. No more cooling is possible. The sun's remnant will be a black dwarf, a cold, dark, inert sphere of crystallized carbon and oxygen drifting through the galaxy forever. But here is the haunting thing about white dwarfs, and the reason they matter to the story of the last star. There is no such thing as a black dwarf yet. The universe is 13.8 billion years old. The oldest white dwarfs are perhaps 13 billion years old, and not one of them has had enough time to cool to the black dwarf stage. The cooling timescales required are so vast, quadrillions of years, that the universe simply hasn't been around long enough. Every white dwarf that has ever formed in the history of the cosmos is still warm, still glowing, however faintly. The black dwarfs are coming, they are inevitable, but they have not arrived yet. This means that right now, in the present era, the universe retains a faint, ghostly luminosity from all the stellar generations that have come before. The galaxy is haunted by the cooling corpses of ancient stars, still warm enough to emit a whisper of infrared radiation. In 1 billion years, this haunting will be slightly cooler. In 1 trillion years, cooler still. But it will persist, at some detectable level for inconceivable spans of time. Now, let's zoom out from our sun and look at what's happening across the galaxy over the next 5 to 10 billion years. The sun's death, as we've described it, is not an isolated event. It is one instance of a process that is happening to tens of billions of sun-like stars throughout the Milky Way and across the observable universe. The G-type and K-type stars, the yellow dwarfs and orange dwarfs that formed in roughly the same cosmic epoch as our Sun, in the great star-forming burst that accompanied the early maturity of the universe, are all on broadly similar schedules. They will all, within the next 5 to 10 billion years, exhaust their core hydrogen, expand to red giants, shed their envelopes, and settle into white dwarfs. This is the first great dimming. Right now, the Milky Way glows with the light of hundreds of billions of stars in a wide range of colours and luminosities. 5 billion years from now, that picture has changed significantly. The most massive stars of the blue and blue-white giants that light up the spiral arms are already gone or nearly gone, their deaths having played out over millions to hundreds of millions of years. The sun-like stars are dying, or recently dead. The galaxy's colour, if you could see it whole from an external vantage point, has shifted. The brilliant blue spiral arms are dark. The galaxy glows in yellows and oranges and reds, the colours of aging sun-like stars in their final active phases, the cooler light of K-type dwarfs, and the deep red of the billions of red dwarfs that were always there but never very visible. And in 10 billion years from now, in an era so remote it is difficult to even contextualize, the transformation is more dramatic. Most of the sun-like stars are done. The galaxy's visible light comes overwhelmingly from red dwarfs and from the cooling remnants of the dead. The white dwarfs, still warm from their stellar lives, contribute a diffuse, faint glow to the galactic background. But the brilliant era of stellar diversity is over. The remaining fires are mostly dim and red, and yet, and this is important, there are still a lot of them. Hundreds of billions of red dwarfs, each one fusing hydrogen at a glacial pace, each one with trillions of years still ahead of it. The galaxy is not dark in 10 billion years, not by any reasonable measure. It is dimmer, certainly, redder, certainly. quieter in terms of the energetic events, the supernovae, the gamma-ray bursts, the spectacular deaths of massive stars that marked the stelliferous era's younger phases. But it is still lit, still burning, still, in the most fundamental sense, alive. The last star hasn't gone out, not even close. But here is the thing about this period, this intermediate epoch between our present and the far future, that most people don't consider. It is not just the stars that are changing, the galaxies are changing too. Right now, the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbour, roughly 2.5 million light-years away, are approaching each other at approximately 110 kilometers per second. They have been approaching for most of the universe's history, and they will collide. The Andromeda collision, formerly called the Milky Way-Andromeda merger, is expected to begin in approximately 4.5 billion years. The word collision is slightly misleading. Galaxies are mostly empty space. When the Milky Way and Andromeda collide, individual stars will almost certainly not actually hit each other. The distances between stars are simply too vast. It will not be an impact in the way two billiard balls impact. It will be a gravitational catastrophe. The two galaxies will pass through each other, their gravitational fields interacting, pulling streams of stars out of their original orbits, distorting the spiral structure of both galaxies into wild, chaotic shapes. The first pass will occur over hundreds of millions of years. Then the two galaxies will swing past each other, interact gravitationally, and come back for another pass, and another. Over the course of perhaps 2 billion years after the first contact, the two galaxies will eventually lose enough orbital energy to each other through these repeated interactions to merge completely. The result will be a single, larger galaxy, sometimes called Milkomeda or Milkdromeda by astronomers, that is no longer a spiral galaxy, but an elliptical one. The beautiful pinwheel structure of the Milky Way, the sweeping arms that have been forming stars for billions of years, will be disrupted and ultimately destroyed. The merged galaxy will settle into a more spherical, less organized shape. The merger will also trigger enormous bursts of star formation as interstellar gas clouds are compressed by the collision. Stars will form in bursts, brilliantly, extravagantly, burning through fuel at rates reminiscent of the early universe's most productive epoch. And then those stars will die, faster than their predecessors, adding more stellar corpses to the accumulating graveyard. When the merger settles, perhaps 6 to 7 billion years from now, the resulting elliptical galaxy will be home to a vast population of white dwarfs and neutron stars and black holes, the remnants of all the stars that burned and died through both galaxies' long histories, plus the surviving red dwarfs still quietly burning, still millennia upon millennia away from their own endings. And at the centre of Milkomeda will be a supermassive black hole, the merged remnants of the Milky Way's Sagittarius A star and Andromeda's own central black hole, combined into an object of perhaps 30 to 40 million solar masses. Briefly, during the merger and the star formation burst that accompanies it, this central black hole may flare to life as a quasar, accreting gas and dust and shining across the universe with the light of billions of suns. Then, as the surrounding material is consumed and the merger settles, it will go quiet again, a sleeping giant at the center of a dimming galaxy. Now, let's talk about something that the countdown makes visible in a way that pure scale videos cannot. The merger of the Milky Way and Andromeda is a beautiful, catastrophic, galactic-scale event. But in the context of the story we're telling, the countdown to the last star, it is a subplot, a dramatic episode in a larger narrative. What matters more, in the long run, is what happens to the red dwarfs through all of this. Red dwarfs are not disrupted by galactic mergers. Not meaningfully. Individual stars can be gravitationally ejected from galaxies during mergers, flung out into intergalactic space by the whiplash dynamics of two massive structures interacting. Some small percentage of red dwarfs will certainly be lost from the merged galaxy during the Milky Way Andromeda collision. They will spend the rest of their lives, trillions of years, drifting through the intergalactic void alone, lit only by their own faint red glow. But most red dwarfs survive the merger intact. They continue burning. The galactic drama occurs around them, through them, but does not fundamentally alter their internal physics. They are too small, too self-contained, too governed by their own stellar dynamics to be much affected by the gravitational ballet of galactic mergers. Red dwarfs burn on, indifferent to the chaos. And this is, in a way, the defining characteristic of red dwarfs, their extraordinary persistence in the face of change. The universe transforms around them. Massive stars are born and die. Galaxies merge. The large-scale structure of the cosmos evolves. And the red dwarfs just keep quietly burning. They will outlast everything we know. Let's pause the timeline here at roughly 10 billion years from now and take stock of what we've lost. In the 10 billion years between our present and this point in the countdown, the universe will have lost every O-type star, the blue giants, the hottest and most massive stellar objects, gone within the first tens of millions of years. Their supernovae will have seeded the interstellar medium with heavy elements, their neutron stars and black holes drifting silently through the galaxy. Every B-type star, the slightly less extreme blue-white giants, gone within the first 100 million years or so. Every A-type star, the bright white stars like Sirius and Vega, gone within the first 2 billion years. Most F-type stars, slightly hotter than the Sun, burning slightly faster, gone or going. Most G-type stars, Sun-like, including our own Sun, gone or in the process of dying, their planetary systems reduced to collections of scorched rocks, orbiting cooling white dwarfs. The spiral structure of the Milky Way disrupted and destroyed by the Andromeda merger, replaced by the more diffuse, less organized structure of an elliptical galaxy. The easy availability of star-forming gas increasingly depleted. The rate of new star formation will have fallen to something approaching zero for the larger star types. Some new red dwarfs may still form from the depleted gas clouds, but the rate is a whisper of what it once was. The habitable zone around our Sun, gone. The inner solar system scorched. Whatever was Earth reduced to either an engulfed fragment or a baked rock orbiting a white dwarf. What remains? Hundreds of billions of cooling white dwarfs, neutron stars and black holes by the billions, the supermassive black hole at the center of Milkomeda, and the red dwarfs. Hundreds of billions of them, maybe more, still burning their slow, patient fires. The universe at 10 billion years from now is dimmer, quieter, redder. The brilliant, energetic, violent stellar life of the young cosmos is largely over. What remains is the long, slow, patient burning of the dim stars, and they have a very long time to go. Here's a question that the countdown makes unavoidable. Could any civilization survive this far? 10 billion years from now, our Sun will be a cooling white dwarf. Earth if it still exists as a discrete object, will be a bare, airless rock orbiting that white dwarf at roughly its current distance. It will be cold, extremely cold, illuminated only by the faint thermal glow of the white dwarf, which will have been cooling for perhaps 5 billion years by this point. Whatever orbital mechanics the red giant phase and the mass lost during the planetary nebula left behind, it will not be Earth as we know it, not even close. But humanity, or whatever humanity becomes in 10 billion years, need not be on Earth. The history of our species is the history of movement, of exploration, of expanding into new environments. 10 billion years is enough time, if we survive, to have spread across the galaxy, to have adapted to countless environments, to have developed technologies and forms of existence that would be utterly unrecognizable to us today. If any form of what we would recognize as biological life persists 10 billion years from now, it almost certainly does so around a red dwarf. Not because red dwarfs are easy places to live and they present real challenges, including their propensity for flaring in their youth and the tidal locking that tends to leave one hemisphere always baked and one always frozen, but because they are the only stars still burning, because their warmth is the only warmth still on offer from active stellar fusion. Because if you want to live near a star-warmed world in 10 billion years, a red dwarf is your only option. And the question of whether any civilization, or biological or digital or something we haven't imagined, might persist for 10 billion years is not a question physics can answer. It is a question of contingency, of luck, of choices made across unimaginable spans of time. It may be that we are the only intelligent life in the universe and we destroy ourselves within the next 1,000 years. It may be that the universe is teeming with intelligence spread across galaxies, and that some form of it will ride out every stellar transition from the first red giant deaths to the last red dwarf flickers. We don't know. But the countdown doesn't care whether anyone is watching. The stars burn and die on their own schedule. The universe follows its physics whether or not there are eyes to see it, minds to mourn it, or civilizations to attempt to survive it. The next phase of the countdown is already locked in. The physics is settled. The timeline is written. 1 trillion years. Write it out in full. 1 trillion years. Say it slowly. Try to feel the weight of it. 1 trillion years from now, the universe will be approximately 72 times older than it is today. Every sun-like star that exists right now, every single one in every galaxy, in every corner of the observable universe, will have died. Their white dwarf remnants will have been cooling for so long that the hottest of them, those that formed most recently, will have dropped to temperatures of a few thousand degrees. The coolest, the oldest, will be barely warm at all. The brilliant, diverse, colourful stellar population of the present universe, the one we see when we look up at the night sky, the one that seeded the interstellar medium with heavy elements, the one that provided the energy for every living thing that has ever existed on every world we know about, will be gone, and the red dwarfs will still be burning. This is the era we're entering now in our countdown, the trillion-year twilight, the epoch when the stelliferous era enters its long, slow, final chapter, not with a dramatic collapse, but with a gradual, patient dimming. A universe that by the standards of its youth is already enormously old, already changed beyond recognition, and yet still lit, still warm in places, still, in the deepest physical sense, alive. This is the age of red dwarfs. To understand what the universe looks like in this era, we first need to understand something fundamental about how red dwarfs age. Sun-like stars have a complicated late life. They expand, they contract, they pulse, they shed their outer layers, they go through multiple burning phases: hydrogen, then helium, then the asymptotic giant branch, then the planetary nebula. It is a messy, dramatic process that transforms a stable, predictable object into a sequence of increasingly exotic configurations before finally leaving behind a white dwarf. Red dwarfs don't do any of that. Red dwarfs are fully convective stars. This means that their entire interior, from the core to the surface, is in constant, turbulent circulation. Unlike the Sun, which has a radiative zone around its core that acts as a barrier separating the core from the convective outer layers, a red dwarf has no such barrier. Yet the entire star is mixed. Hydrogen from the outer layers is constantly being pulled down toward the core. Helium produced by fusion in the core is constantly being mixed back outward. The star is, in a sense, continuously stirring itself. This has a profound consequence. A red dwarf can access essentially all of its hydrogen fuel, not just the hydrogen in the core. Our Sun, because its interior is stratified, can only fuse the hydrogen in and near its core, perhaps 10% of its total hydrogen supply. When the core hydrogen runs out, the Sun's active life is over. Even though 90% of its hydrogen remains in the outer layers, where it cannot be reached by the fusion reactions. A red dwarf faces no such limitation. It burns all the way down to the dregs. This is why red dwarfs live so long. Not just because they burn slowly, but because they burn efficiently, using nearly all of their available fuel before finally running out. And when a red dwarf finally does run out of hydrogen, it doesn't expand into a red giant, it doesn't shed a planetary nebula, it doesn't go through a helium-burning phase. The physics of its low mass simply doesn't allow those transitions. Instead, a red dwarf just slowly dims. As the hydrogen in its core depletes, fusion gradually slows. The star contracts slightly, heats up slightly, becoming briefly bluer and more luminous in an interesting paradox, and then, as the fuel truly runs out, fades. It cools. It shrinks. It becomes a white dwarf, but one made not of carbon and oxygen like the remnants of sun-like stars, but of helium, the product of all that slow, patient hydrogen fusion. A helium white dwarf, a quiet corpse. Oh, no explosion, no nebula, no drama, just a slow fade to dark. Let's set the scene for the trillion-year twilight. We're 1 trillion years into the future. The universe has entered a phase that cosmologists, following the framework established by Fred Adams and Greg Laughlin in their foundational work, The 5 Ages of the Universe, sometimes call the later stelliferous era, the period after the massive and intermediate stars are gone, but before the last red dwarf dies. What does a galaxy look like in this era? First, there are no spiral galaxies anymore. The Milky Way-Andromeda merger happened 8 to 9 billion years ago in this timeline. By the time we reach 1 trillion years, the merged Milkomeda galaxy will have had almost 994 billion years to settle into its elliptical form. But by this point, many galaxies have continued to merge with each other. The large-scale structure of the universe, the cosmic web of filaments and voids and galaxy clusters that was so prominent in the early universe, has continued to evolve. Galaxy clusters have drawn closer together through gravity. Smaller galaxies have been absorbed by larger ones. The universe at 1 trillion years is populated by enormous, diffuse, elliptical galaxies, bloated structures containing the remnants of hundreds of generations of star formation, dotted with the faint red lights of surviving red dwarfs and the cooling embers of white dwarfs. Second, the expansion of the universe has continued. The universe is not static. It is expanding, driven by dark energy, the mysterious component of the universe that appears to be causing the expansion to accelerate. At 1 trillion years from now, the expansion will have been accelerating for essentially the entire trillion years of elapsed time. Galaxies that are not gravitationally bound to each other, galaxies in other clusters, other groups, will have receded so far that their light can no longer reach us. The observable universe, in the sense of the region from which light can theoretically arrive at our location, will have shrunk dramatically compared to today. This is one of the eerier aspects of the very long future. We are currently in something of a privileged moment in cosmic history, a time when we can look out and see the light of galaxies across the entire observable universe, including galaxies from the early universe whose ancient light is only now reaching us. In 1 trillion years, that view will be gone. The expansion of space will have carried most galaxies beyond the cosmological horizon. Our galaxy, or whatever it has become, will be essentially alone in the observable universe, surrounded by darkness. The universe will be lonely in a way it isn't today. Third, and most importantly, the sky from any hypothetical vantage point within our galaxy will look fundamentally different from what we see tonight. There are no blue stars, no white stars, no yellow stars. The sun-like stars are gone, their remnants cooling in the dark. The only active stars, the only objects still fusing hydrogen, are red. Deep, burning red and orange-red. The galaxy glows with a dim, ruddy light. Like the embers of a fire that has been burning for so long the wood has nearly run out. This is the universe's twilight. Not the end, not yet. But the quality of the light has changed. The energy of youth is gone. What remains is the long, patient warmth of stars that were never in a hurry. Let's talk about the red dwarfs themselves in more detail, because they are the protagonists of this era. Red dwarfs come in a range of sizes and their lifespans vary accordingly. The more massive red dwarfs, those with 40 to 50% of the Sun's mass, the upper end of the red dwarf range, will actually be the first to go. They have more fuel, but they also burn it slightly faster. Their lifespans are estimated at roughly 1 to 2 trillion years. By 1 trillion years from now, the upper end of the red dwarf population will be starting to run out of fuel. The first red dwarf deaths will be occurring, not in any way visible to human intuition, not as dramatic events, but as slow, quiet fadings. These early dying red dwarfs will contract, heat slightly in a last brief flare of their lives, and then fade to helium-white dwarfs. No fireworks, no planetary nebulae, just a dimming. Like a light on a rheostat being turned slowly to zero. As the trillion-year epoch progresses, this dimming will work its way down through the red dwarf population. The more massive ones first, then the mid-size ones, then the smallest, the dimmest, the most fuel-efficient. Each successive generation lives longer than the last, in smaller and smaller stellar objects, burning more and more slowly, approaching but never quite reaching the theoretical minimum for hydrogen fusion. The minimum mass for a hydrogen-fusing star is about 7.5% of the Sun's mass, roughly 0.075 solar masses. Below this threshold, the pressure and temperature at the center of the object never becomes sufficient to ignite hydrogen fusion. Objects below this mass are brown dwarfs, failed stars. and objects that glow faintly with heat from gravitational contraction but never truly ignite. The smallest objects that do ignite, those right at the 7.5% threshold, have estimated lifespans approaching 12 trillion years. Some theoretical estimates push as high as 15 trillion years for the absolute minimum stellar mass. These smallest, dimmest, most slow-burning red dwarfs are the finalists in the countdown. They are the last ones standing. And they will stand, burning their miserly hydrogen fuel one proton at a time for 12 trillion years. Here's something worth sitting with. The universe right now, at 13.8 billion years old, has been around for roughly 0.1% of the lifespan of one of those small red dwarfs. Not 0.1% of its total lifespan, 0.1% of the lifespan of a single individual star. Everything that has happened in the history of the observable universe, the Big Bang, the formation of the first stars, the ignition of galaxies, the emergence of life on Earth, the entirety of human history, and whatever comes after, all of it fits in the first 1/10 of the life of a particular class of star that makes up the majority of stars in the cosmos. The universe is not old. The universe is barely past its first morning. This is the temporal vertigo at the heart of this countdown. We tend to think of 13.8 billion years as inconceivably ancient, and by any human standard, it is. But measured against the full lifespan of the cosmos, measured against the trillion-year twilight we're now walking through, 13.8 billion years is a cosmic infancy. The universe has barely warmed up. Let's advance the timeline forward through the trillion-year era and watch what changes. At 2 trillion years, the upper tier of red dwarfs is largely gone. The sky, from any hypothetical observation point, shows fewer active stellar fires. The remaining red dwarfs are smaller, dimmer, slower burning. The average luminosity of the typical active star has dropped significantly. The galaxy is darker than it was at 1 trillion years, which was already dramatically darker than it was at our present moment. The white dwarf population, meanwhile, has been growing for trillions of years. There are now more dead stars, white dwarfs, than there are living ones. The galaxy's mass is increasingly locked up in stellar remnants, white dwarfs, neutron stars, black holes. The living stars are outnumbered by their own ghosts. At 3 trillion years, this trend has continued. The mid-size red dwarfs are entering their final phases. More red dwarf deaths, more helium-white dwarfs joining the cooling population of stellar remnants. The remaining active stars are the smallest, dimmest, most fuel-efficient objects in the universe. The galaxy's luminosity, its total light output, is a small fraction of what it was at our present moment, and something else is changing too. The galaxy's structure is becoming increasingly dominated by its central black hole. Black holes are patient in a way that almost nothing else in the universe can match. The supermassive black hole at the center of Milkomeda, formed from the merger of the Milky Way's and Andromeda's central black holes, contains tens of millions of solar masses. In the early universe, black holes like this were active, voracious things, accreting gas and dust and stars, shining as quasars or active galactic nuclei, radiating enormous energy. But as the gas supply in the galaxy depletes, used up by generations of star formation expelled by stellar winds and supernovae, the supermassive black hole runs out of food. Its accretion disk dries up. It goes quiet. A quiet black hole does almost nothing. It sits at the galactic center. exerting gravitational influence, occasionally capturing a star that wanders too close but otherwise inert. For the trillion-year twilight, it is just the massive anchor at the center of an increasingly dim galaxy. Smaller black holes, stellar mass black holes formed from the deaths of massive stars early in the universe's history, drift through the galaxy like invisible bullets. They emit almost no radiation. They are detectable only by their gravitational effects, and they will persist, essentially unchanged, for far longer than any star. Black holes, according to our best physics, do evaporate. Stephen Hawking's theoretical work in the 1970s predicted that black holes slowly emit thermal radiation, now called Hawking radiation, due to quantum effects at the event horizon. This process causes a black hole to lose mass very, very slowly until it eventually evaporates entirely. But the timescale for Hawking evaporation is almost unimaginably long. A stellar mass black hole, one of the 10 solar mass variety formed from the death of a massive star, would take approximately 10 to the power of 74 years to evaporate. A supermassive black hole of 1,000,000 solar masses would take approximately 10 to the power of 83 years. These numbers are so much larger than the trillion-year timescale we're currently discussing that they are essentially irrelevant to the story of the last star. Black holes will persist, essentially unchanged, through the entire stelliferous era, and far, far beyond. They are not the subject of this countdown. The last star dies long before the first black hole evaporates. Let's talk about something that becomes increasingly important as the trillion-year twilight progresses. The question of stellar nurseries. New stars require raw material, primarily hydrogen gas, in the form of molecular clouds, nebulae, the diffuse interstellar medium. As generations of stars form and die, this raw material is consumed, transformed, and dispersed. The heavier elements, carbon, nitrogen, oxygen, d-ion, that are synthesized in stellar interiors and expelled in stellar deaths don't collapse easily into new stars. They fragment the cooling gas clouds. They change the chemistry of the interstellar medium in ways that make star formation more complex. Over trillions of years, the universe's supply of pristine hydrogen gas, the fuel for star formation, becomes increasingly depleted. This is not an abrupt transition. It is a gradual exhaustion, like a bank account slowly drawn down by small withdrawals over a very long period. But by the time we reach several trillion years into the future, the rate of new star formation, already at a tiny fraction of its peak in our present era, will have approached zero. No new stars are forming. The only stars in the universe are the ones that are still burning from previous generations, and they are one by one using up the last of their fuel and going out. This is a crucial transition in the countdown, because as long as new stars are forming, the stellar population, while declining, is at least being partially replenished. Even if the replenishment rate is tiny, there is still a process actively working to maintain the stellar count. Once that process stops, once the last new star forms from the last available cloud of star-forming gas, the countdown becomes purely a one-way drain. The only direction is down. The only trajectory is toward darkness. The cessation of star formation is the moment when the death of the last star becomes truly inevitable, not merely projected. Before that point, in theory, conditions could change. More gas could become available, star formation could resume. After that point, if there is no recovery, the population of stars can only shrink. In the trillion-year twilight, Something else happens that is worth examining in detail: the fate of planetary systems. By the time we reach the deep red dwarf era, 1 trillion years or more from now, many of the planetary systems that formed alongside their host stars billions of years earlier will have been disrupted. Planetary systems are not eternal. They are held together by the gravity of their host stars, but they are subject to ongoing gravitational perturbations from other stars passing nearby, from the host star's own evolution, from the interactions between the planets themselves. Over billions and trillions of years, these perturbations accumulate. Planets can be ejected from their systems in gravitational slingshot events. They can drift to different orbital distances. They can collide with each other or be absorbed by the host star. The estimated timescale for most planetary systems to be disrupted by gravitational scattering events, either by close stellar encounters or by internal orbital instabilities, is somewhere in the range of 10 to the power of 15 years. That's a quadrillion years, far longer than the lifespan of even the most long-lived red dwarfs. This means that for the entire duration of the stelliferous era, most planetary systems around red dwarfs will remain more or less intact. Their planets won't be in exactly the same orbits they started in. Small perturbations accumulate over time, but the systems will persist as coherent structures, with worlds orbiting their host stars. Which means that during the trillion-year twilight, when the smallest red dwarfs are still burning, there are still planetary systems, still worlds, still the infrastructure, at least, for whatever form life might take in this era. Whether any of those worlds are actually inhabited, whether life could persist for trillions of years around a red dwarf, is one of the most profound questions that this countdown raises, and it deserves careful consideration. Could life survive in the trillion-year twilight? The challenges are real. Red dwarf planets face unique difficulties that Earth-like worlds around Sun-like stars do not. The most well-known challenge is tidal locking, a planet in the habitable zone of a red dwarf, which, because red dwarfs are so dim, must orbit very close to its star, and often within a distance comparable to Mercury's distance from the Sun, is subject to strong tidal forces. Over billions of years, these tidal forces synchronize the planet's rotation with its orbital period, so that the same hemisphere always faces the star. One side perpetually baked by the star's light, one side permanently frozen in darkness. This sounds inhospitable, and in some configurations it is, but theoretical models suggest that tidal locking doesn't necessarily make a planet uninhabitable. If the planet has an atmosphere thick enough to redistribute heat, if winds can carry warmth from the day side to the night side, then a habitable band might exist near the terminator, the boundary between the permanent day and permanent night hemispheres. Life in this band would experience a sky that never changes, a sun that hangs forever at the horizon, a twilight that never ends, a trillion-year twilight, in a very literal sense. The second major challenge is stellar flares. Young red dwarfs, in their first billion years or so, are prone to enormous flares, eruptions of ultraviolet and X-ray radiation that can be orders of magnitude more intense than anything our Sun produces. These flares can strip away planetary atmospheres if the planet lacks a strong magnetic field, and can be lethal to surface life. This is a serious problem, and it may mean that life on red dwarf planets can only emerge after the star has settled into a quieter middle age. But red dwarfs do settle down. After the first billion years or so, their flare activity decreases significantly, and 1 billion years is nothing compared to a trillion-year lifespan. If life can establish itself on a red dwarf planet during the star's quiet middle age, after the intense early flaring, but before the long decline of the final phase, it has trillions of years of stable, low-energy stellar output in which to evolve, develop, expand. Life on Earth has had about 3.8 billion years to go from single-celled organisms to technological civilization. Life around a mid-sized red dwarf might have 1,000 times that window. What does life become in 1,000 times the age of Earth's biosphere? What does intelligence look like after 1 trillion years of development? These are questions that no physics can answer, only imagination. But the countdown does not foreclose them. The physics permits them. The time exists. Now let's talk about the 5 trillion-year mark, roughly where the countdown enters its deepest and most significant phase. By 5 trillion years from now, the universe is a profoundly different place. The galaxy, Milkomeda, the merged remnant of our galaxy and Andromeda, is immense and diffuse. Its outer reaches are populated by drifting stellar remnants, white dwarfs cooling toward their eventual black dwarf state, neutron stars spinning down their rotation rates over billions of years, stellar mass black holes drifting silently through the dark. In the far outer halo, ejected stars, red dwarfs and white dwarfs flung out by gravitational interactions over the preceding trillions of years, drift in solitary orbits separated from the main galaxy by vast distances. The central regions of the galaxy are dominated by the supermassive black hole, now perhaps tens of millions of solar masses after billions of years of occasional stellar captures. Surrounding it a dense population of stellar remnants orbiting in a tight cluster, the galactic nucleus stripped of most of its living stars but still gravitationally active. And scattered through the galaxy, in their hundreds of billions, the surviving red dwarfs. The smaller ones, the ones at 10 to 15% of solar mass, still have trillions of years ahead of them. But the larger red dwarfs, those that started their lives at 40 to 50% of solar mass, are dying now. Their hydrogen is running out, one by one, over time scales of billions of years each. They are contracting, briefly brightening, and then fading to helium-white dwarfs. The galaxy, at 5 trillion years, is like a great bonfire on a cold night, 5 hours after it was at its peak. The big logs, the massive, energetic stellar objects of the young universe burned out hours ago. The medium logs, the sun-like stars, burned out more recently, their embers still faintly glowing in the form of cooling white dwarfs. What remains in the fire now are the small, dense pieces, the red dwarfs, burning low and red, shedding warmth at a fraction of the original intensity, but persistent. Patient. The fire is still going, but you can feel how the night is deepening. Here's something that the countdown makes visible that most discussions of cosmology miss. The death of a red dwarf is not a dramatic event by any standard measure. There is no explosion. There is no expansion to a size that could engulf planets. There is no spectacular nebula. But for any civilization living on a planet orbiting a dying red dwarf, and there may be such civilizations if life persists into this era, it is the most catastrophic possible event. Because the death of a red dwarf is slow. It plays out over billions of years. The star doesn't go out suddenly. It dims. Gradually, imperceptibly, on human timescales imperceptibly, though on geological timescales the change accumulates. The habitable zone migrates inward as the star's luminosity drops. Planets that were once comfortably warm grow cooler. Oceans cool. Atmospheric circulation patterns change. Ice accumulates at the poles, then spreads toward the equator. The sky darkens. And for any civilization intelligent enough to understand what is happening, and any civilization that has had trillions of years to develop would surely understand, this is the ultimate slow-motion catastrophe. Not an asteroid impact, not a gamma-ray burst, not a sudden stellar explosion. Just a slow, inexorable dimming, a dying of the light that plays out over geological timescales that could potentially be seen coming billions of years in advance. Would they try to adapt? Would they migrate to another star system? Would they try to engineer their star into a longer life, somehow feeding it additional hydrogen, disrupting its convective mixing, altering its fusion rate? We have theories, ideas, speculations, but no answers. What we know is that the physics gives them time, an enormous amount of time. More time than any organism or civilization has ever had. Whether time is enough depends on what they do with it. Let's end part 3 with a number that should change how you feel about where we are in the timeline. We are, right now, at the very beginning of the universe's middle age. The stelliferous era has roughly 100 trillion years to run. We are 13.8 billion years in, less than 0.02% of the way through. The trillion-year twilight we've been walking through in this part of the countdown, that era of dim red dwarfs and cooling white dwarfs and empty dark galaxies, is the universe's long, patient afternoon. The era between the energetic morning and the cold, starless night. And it is coming. Not fast. Not on any time scale that means anything to a human life, or a civilization, or even a geological epoch. But as surely as the laws of physics hold, and they have held for 13.8 billion years without exception, it is coming. The last star will burn out. It will be a red dwarf, tiny and dim and ancient. It will have been burning for 12 trillion years. It will have outlasted everything that preceded it, every galaxy, every planet, every civilization, every structure that stellar energy ever made possible. And when it goes out, when the last fusion reaction in the last stellar core finally sputters to nothing, the stelliferous era will end. We are now in the final chapter of the Age of Stars, not the final pages. Not the final paragraph, the final chapter, a chapter that itself spans trillions of years, that contains more time within it than all the previous chapters combined, and that ends with a darkness so complete and so permanent that no subsequent chapter will ever be lit by stellar fire again. We have walked through the death of the massive stars, the death of our sun, the slow attrition of the red giant phase washing across the galactic population of sun-like stars. We have walked through the trillion-year twilight, the era of red dwarf dominance, the long, patient burning of the universe's smallest stellar fires. We have watched the galaxy transform from a brilliant, diverse, energetic structure into a dim, red-lit, aging system populated mostly by stellar corpses and the handful of surviving red dwarfs still fusing their last hydrogen reserves. Now, we enter the final phase of the countdown, the last 10 trillion years of the stelliferous era. Let's establish the baseline. At roughly 10 trillion years from now, the approximate point where this final phase begins, the universe's stellar population has been dramatically reduced from its peak. The most massive red dwarfs have already died. The remaining active stars are exclusively the smallest, dimmest, most miserly hydrogen burners in the universe, objects at the very lower boundary of what physics permits to be called a star at all. These are the ultra-cool red dwarfs, objects with masses between 7.5 and perhaps 20% of the Sun's mass. Their surface temperatures range from approximately 2,000 to perhaps 3,000 degrees Kelvin, so cool that their spectra peak in deep red and near infrared light. They shine with a warmth you could almost feel rather than see. A reddish glow that would look more like the coils of an electric heater than anything we associate with stars. They are extraordinarily dim. TRAPPIST-1, with its mass of about 8% of the Sun's mass, shines at roughly 0.05% of the Sun's luminosity. A planet in the habitable zone of TRAPPIST-1 orbits at roughly 4% of the Earth-Sun distance, closer to TRAPPIST-1 than Mercury is to our Sun, and still receives only a modest amount of energy. The day sky from such a planet would appear much dimmer than our own, the star a small, deep red disk hanging in a sky that would seem perpetually twilit even at local noon. These are the last stars. These are the objects whose deaths define the end of everything, and at 10 trillion years from now, they still have up to 2 trillion years ahead of them. Let's walk through what the galaxy looks like as we enter this final phase. The structure we would recognize as a galaxy, the organized gravitational system that we call the Milky Way, will still exist at 10 trillion years, in a broad sense. The gravitational well of the central supermassive black hole still holds things together. The remaining stellar remnants and the surviving red dwarfs are still in orbit around the galactic center. The galaxy persists, though it is dim and diffuse beyond anything we could see with the naked eye from our current vantage. But the galaxy has been slowly losing members for trillions of years. There is a physical process called gravitational relaxation, or sometimes stellar evaporation, that causes galaxies to very slowly lose stars over time. The mechanism is subtle. Random gravitational interactions between stars, close encounters, near misses, can exchange energy between them. In a statistical sense, some stars gain energy from these interactions, and some lose energy. Stars that gain enough energy can become unbound from the galaxy entirely. They achieve escape velocity and drift off into intergalactic space. Stars that lose energy sink deeper into the gravitational well, moving toward the center. This process is slow, extremely slow. On time scales comparable to the current age of the universe, it is negligible, but on time scales of trillions of years, it is not negligible at all. Over very long periods, a gravitationally bound system like a galaxy will slowly evaporate, shedding stars from its outer edges into intergalactic space, while the remaining stars sink toward the center. The estimated timescale for a galaxy to lose a significant fraction of its stars through this evaporation process is roughly 10 to the power of 19 to 10 to the power of 20 years, 10 to 100 quintillion years. This is far longer than the lifespan of the last red dwarf, which means that the process of galactic evaporation is occurring during the final phase of the stelliferous era, but has not yet run to completion when the last star dies. What this means practically: at 10 trillion years from now, the galaxy still exists as a bound structure. Many of its red dwarfs are still orbiting within it, but some percentage, perhaps a few percent of the original population, have been evaporated away over the preceding trillions of years, drifting alone through the intergalactic void. These solitary red dwarfs, cut loose from their home galaxy, will burn on just as long as their cousins inside the galaxy. They are just more isolated, more alone. If any of them have planets, and many of them will, those planets exist in complete and total darkness beyond the light of their own star. No galaxy, no background glow of distant stellar populations, just the single dim ember of their host star, surrounded by the void. Now, let's talk about something that happens in the very deep future that is strange and worth understanding. As the final red dwarfs age, as they move through their last trillion years of hydrogen fusion, they undergo a slow transformation that changes their character in an unexpected way. Remember that red dwarfs are fully convective. Their entire interior is mixed. This means that as they fuse hydrogen into helium, the helium is distributed throughout the star rather than accumulating in the core. The star's composition gradually changes from nearly pure hydrogen at birth to an increasingly helium-rich mixture as it ages. The ratio of helium to hydrogen increases slowly, decade by decade, millennium by millennium, over trillions of years. As the helium fraction increases, the star's behavior subtly changes. Helium is heavier than hydrogen, and a helium-rich stellar interior behaves differently under the physics of hydrostatic equilibrium. The star contracts slightly. Its surface temperature rises slightly. In the very late stages of a red dwarf's life, in the final hundreds of billions of years, a curious thing happens. The star actually becomes hotter and bluer than it was in its prime. This is the blue dwarf phase. As the red dwarf nears the exhaustion of its hydrogen supply, in the last few percent of its total lifespan, its surface temperature climbs from the deep red of a young red dwarf toward a warmer orange, then yellow, then potentially a pale blue-white. For a brief window, cosmologically speaking, a few tens or hundreds of billions of years, the dying red dwarf shines more brightly and with a different color than it has for most of its existence. This is counterintuitive. We expect things to cool as they die. The red dwarf's final phase defies that expectation. Before it fades, it briefly blooms. This has an extraordinary consequence for any hypothetical life or civilization in a red dwarf system. For most of the star's life, the habitable zone sits very close to the star because the star is so dim that only planets orbiting nearby receive enough energy for liquid water. But as the star brightens in its blue dwarf phase, the habitable zone migrates outward. Planets that were previously too far from the star to be warm enough might, for the first time in their existence, find themselves in the habitable zone. Frozen worlds that have been locked in ice for trillions of years might thaw. Whether any of this leads to life emerging for the first time, or whether previously too cold worlds become briefly habitable to life that migrated there, is unknowable. But the physics does not foreclose it. The last trillion years of a red dwarf's life include a phase where its habitable zone briefly sweeps outward, only potentially illuminating worlds that have never before seen liquid water. A brief, strange, late-life warmth, a last gift of energy before the long dark. Let's count down through specific milestones in this final phase. At 10 trillion years, the galaxy is dim, red, and aging. The surviving stars are all ultra-cool red dwarfs. The largest of these are already in their blue dwarf phase, their hydrogen running out, their surfaces warming paradoxically. White dwarfs, by the hundreds of billions, drift through the galaxy, cooling infinitesimally slowly. At 11 trillion years, more red dwarfs have completed their blue dwarf phase and faded to helium-white dwarfs. The total number of active stars has fallen significantly from the 10 trillion year baseline. In the galaxy's light output is a small fraction of what it was, even at the beginning of this final phase. But there are still billions of active stellar fires. At 12 trillion years, we are approaching the outer edge of the estimated lifespan range for the most long-lived red dwarfs. The smallest stellar objects, those right at the hydrogen fusion threshold, 7.5% of solar mass, are entering their final billions of years. Their hydrogen fuel is becoming critically depleted. They have perhaps 1 trillion years left, perhaps less. The countdown is now measurable in something closer to just trillions, rather than many trillions. At 15 trillion years, most estimates for even the most long-lived red dwarfs place their deaths before this point. Some models stretch to this range, but the certainty decreases with the extremes of the timeline. By 15 trillion years, there are very few active stars left in the universe. Perhaps thousands, perhaps millions, if the population of minimal mass red dwarfs is larger than current models suggest, but not billions, not hundreds of billions. The age of stars is ending. Let's talk about the last red dwarfs specifically, what we know about objects at the very bottom of the stellar mass range. The theoretical lower limit for hydrogen fusion, the absolute minimum mass that allows an object to fuse hydrogen under any conditions, is about 0.075 solar masses, or 75 Jupiter masses. Objects below this mass, brown dwarfs, can fuse deuterium briefly in their early lives, or lithium, but cannot sustain proton-proton hydrogen fusion, which is the slow, seen primary fuel source that gives main sequence stars their extraordinary longevity. Objects right at this threshold, 0.075 to 0.08 solar masses, are in a borderline zone. Some of them may fuse hydrogen so slowly and intermittently that their stellar lifespan is difficult to define precisely. They sit at the boundary between true stars and failed stars, and their estimated longevity approaches or possibly exceeds 10 to 12 trillion years. We have actually observed a few stars very close to this mass limit. VB10, also known as Van Biesbroek's star, has a mass of about 0.075 solar masses, barely above the hydrogen fusion threshold. It is so dim that it has a luminosity of about 0.01% of the Sun's. It was for a long time the faintest known star. From the distance of a habitable zone planet, its disk would be extraordinarily small and dim, more like a bright planet than a star, casting shadows only dimly on any surface it illuminated. VB10's estimated lifespan is difficult to calculate precisely because it sits so close to the boundary, but it is certainly in the multi-trillion-year range. It will still be fusing hydrogen, however intermittently, however slowly, long after every sun-like star in the observable universe has died. Objects like VB10 are the last stars. They are the dim, ancient, barely burning embers at the bottom of the stellar mass range, and they will be the last to go out. What does the universe look like in the final billion years of the stelliferous era? This is perhaps the most alien landscape in the entire countdown. It is a universe so transformed from what we know that describing it requires stripping away almost every assumption we carry about what space looks like. The observable universe, the region from which light can, in principle, reach any given point, is dramatically smaller than it is today. The accelerating expansion of space has pushed virtually all external galaxies beyond the cosmological horizon. Not just the distant galaxies, even nearby galaxy clusters, those hundreds of millions of light years away, are by now inaccessible. The universe, from any vantage point, appears as a small, isolated gravitational system surrounded by absolute darkness. Within what remains of our galaxy, the scene is stark. The dominant objects are the stellar remnants, white dwarfs in various stages of cooling, neutron stars spinning slowly and emitting only faint remnant radiation, black holes of all sizes drifting silently through the dark. The supermassive black hole at the galactic center sits inert, its accretion disk long since gone, accreting matter only from the occasional stellar remnant that wanders too close. And somewhere in this landscape, scattered through the galaxy in decreasing numbers, dim and red and ancient, the last red dwarfs are burning out. There is no dramatic moment, there is no event horizon in the countdown where you can say, now the last star has died. Stars do not go out like candles, they fade. The transition from active hydrogen fusion to inert helium white dwarf is gradual, playing out over millions or billions of years for even the smallest red dwarfs. But there is a last moment of fusion, a last proton-proton reaction, a last photon produced in the core of a star by nuclear fire, working its way outward through the stellar interior, eventually emerging into space. And then nothing. Here's something worth understanding about what nothing means in this context. When the last red dwarf dies, when the last fusion reaction in the last stellar core stops, the universe does not go dark instantaneously. The star's remnant, the helium white dwarf left behind, is still hot. It will radiate heat for an extraordinarily long time. The white dwarfs of sun-like stars formed 12 trillion years earlier are still warm, cooling, always cooling, but not yet dark. There is a cascade of fading, not a single switch being thrown. But the character of the darkness that follows is qualitatively different from anything that came before. Because every previous period of darkness in the universe, the dark era before the first stars, the dark voids between galaxies, was surrounded by, or adjacent to, or destined to be replaced by stellar light. The universe before the first stars ignited was dark, but it was a darkness pregnant with the future. The gas clouds were collapsing, the first fires were forming. The darkness was temporary. The darkness after the last star goes out is different, it is permanent. No new stars will form. The raw material is exhausted, converted into stellar remnants and heavy elements, and the diffuse plasma of the intergalactic medium. The conditions that allowed stellar ignition, dense clouds of pristine hydrogen, perturbations to trigger their collapse, the physics of gravitational contraction, will never recur. And the darkness after the last star is the darkness of true ending, not a pause, not a transition, an ending. Let's ask the hardest question the countdown forces on us. Is there anyone still there? When the last red dwarf enters its final phase, when it has perhaps 1 billion years left, perhaps less, is there any form of consciousness, any civilization, any intelligence in the universe that is aware of what is happening? We cannot know, but we can reason about the possibilities. There are broadly 3 scenarios. The first scenario: life never persisted beyond the stelliferous era's early phases. The universe is, has been, and will be essentially lifeless beyond the next few billion years. Whatever civilizations arose, including perhaps our own descendants, failed to persist, failed to adapt. He failed to survive the transitions between stellar epochs. The last star burns out unwatched, unmourned, its death witnessed only by the physics that governs it. The second scenario: life existed for a very long time around red dwarfs, perhaps for hundreds of billions of years, But the diminishing energy environment eventually made the maintenance of complex organization impossible. Life requires energy gradients. As the remaining stars dim and cool, as the energy available from stellar sources decreases, as the universe approaches thermodynamic equilibrium, the conditions for life become increasingly constrained. Perhaps intelligent life persisted for 1 trillion years, 2 trillion years. But the last few trillion years of the stelliferous era are simply too cold, too dark. It's too energy poor to sustain anything complex enough to call itself aware. In this scenario, there was once awareness in the universe, for a span of time dwarfing the age of our current civilization by a factor of trillions. And then it ended. Not with a bang, but with the gradual failure of the energy gradient that sustained it. The third scenario, intelligence adapted, not once, not twice, but continuously over trillions of years. Life around red dwarfs learned to manage stellar energy with extraordinary efficiency. Civilizations became radically different from what we would recognize, optimized not for the energy-rich environment of a sun-like star, but for the miserly trickle of energy from a dim red ember. Perhaps consciousness itself evolved toward forms that required very little energy, slower, colder, but persistent. A kind of metabolism operating on geological timescales rather than biological ones, a form of thought so slow that a single idea plays out over 1 million years, but a form of thought nonetheless. In this scenario, there is someone watching when the last star begins its final dimming. There is awareness in the universe when the last fusion reaction occurs, and there is a civilization, unrecognizable to us, almost certainly, but real, that faces the end of the age of stars, with whatever wisdom and grief and pragmatism trillions of years of existence can provide. We cannot know which of these scenarios is true. We may never know, but the countdown holds space for all three. The physics permits each of them. The universe, in its long patience, does not foreclose any of these possibilities from the outside. Only history, playing out over the next 12 trillion years, will determine which one actually occurs. Let's zoom in on the very end of the countdown. Somewhere around 12 trillion years from now, the estimates vary depending on how the smallest red dwarfs behave at the absolute edge of the stellar mass range, and on details of their internal physics that our current models don't fully resolve. The last star is approaching its death. It has been burning for 12 trillion years. To put that in perspective, if the current age of the universe were a single day, the lifespan of the last star would be approximately 3 years and 2 months. Everything we know, everything that has ever happened in the history of the observable cosmos fits into the first 8 hours of the first day of a 3-year story. The last star is small, very small. Perhaps 8% of the Sun's mass, perhaps slightly less. Its luminosity, for most of its life, was less than 0.01% of the Sun's. It burned its hydrogen with extraordinary care, converting each proton with the slow deliberation of a process that doesn't know urgency. In its final phase, the blue dwarf transitioned, and it has been warming, slightly. Its surface temperature has risen from perhaps 2,500 degrees Kelvin in its prime to perhaps 5,000 or 6,000 degrees now. It shines with a warm yellow-white light, a strange and temporary beauty in the deep twilight of a dying universe. If any worlds orbit it, and there may be worlds, rocky or icy or somewhere between, that have orbited this star since it formed 12 trillion years ago, those worlds have experienced a brief anomalous warmth in their last phase of stellar companionship. But the hydrogen is almost gone. The fusion reactions are slowing. The energy output is declining. The blue dwarf phase is ending. What comes next is the final fading. The last star doesn't die at a single moment. Over the course of billions of years, even as it runs out of hydrogen fuel, the last red dwarf contracts. Its outer layers begin to lose their connection to the fusion core. The energy generation falls below the threshold needed to maintain the star's current structure. The star shrinks, its surface area decreases, its luminosity falls. If you were watching from a nearby planet, if there was a planet and if there was something capable of watching, the change would be imperceptible in any single lifetime, even in any civilization's recorded history, assuming that history spans only millions of years. The star would simply look slightly dimmer from one geological epoch to the next, slightly cooler, slightly smaller. Over billions of years, the change accumulates. The star's surface cools back down from the warmth of the blue dwarf phase, through yellow and orange and back to red, deeper red than before, darker. The habitable zone which swept outward during the blue dwarf phase recedes again, migrating inward as the star dims, abandoning any worlds that had briefly been warmed. The last planets that were habitable, in the narrow sense of liquid water being possible, will freeze again, one by one. Oceans ice over, atmospheres, if they remain, cool and thin. The twilight deepens. The star's fusion is now occurring only intermittently, in brief pulses as pockets of residual hydrogen interact in the cooling core. And the energy output is a ghost of what it was. The stellar wind that pushed outward from the star for trillions of years has died away to almost nothing. And then, at some specific moment in some specific location deep in the stellar core, among a specific set of atomic nuclei, the last proton-proton fusion reaction occurs. 2 hydrogen nuclei, one final collision, one final brief release of energy. A photon created in the depths of the last stellar interior. That photon works its way outward through the contracting star. It takes perhaps 100,000 years, even in this small, dense object, to make its way from the core to the surface. And then it emerges into space, a single photon of deep red light carrying the last nuclear energy the universe will ever produce. It travels outward at the speed of light, through the cold, to dark space around the last star, past whatever frozen worlds orbit in the dark, past the slowly evaporating remains of a galaxy that once contained hundreds of billions of fires, out into the intergalactic void, out toward whatever might be watching, if anything is watching at all. Behind it, the last star continues to collapse. Without fusion to support it against gravity, it contracts. Its surface cools. Its light fades. Over millions of years, it shrinks to the size of a white dwarf, a helium-white dwarf this time, the final product of 12 trillion years of careful, patient hydrogen burning, still warm, still glowing, barely, but no longer a star. The stelliferous era is over. Let's take a moment, right here, at the edge of the end, to appreciate the scale of what has just happened. The stelliferous era lasted approximately 100 trillion years, give or take the uncertainties in our estimates of the smallest red dwarf lifespans. In that time, something on the order of 10 to the 23rd power stars burned. 100 sextillion stellar fires, each one a nuclear furnace, each one a potential source of warmth for whatever worlds orbited it. The universe, for 100 trillion years, was lit. It was not always brilliantly lit. In the early phases, it blazed with the energetic fires of massive young stars. In the middle phases, it glowed with the warm, diverse light of sun-like stars in their prime. In the later phases, it dimmed to the deep red of red dwarfs, quieter and colder, but persistent. In the final phase, it burned with the last fires at the very bottom of the stellar mass range, fires so dim that you could have stared at them from a moderate distance and not been certain you were looking at a star, but it was lit. And in the course of that 100 trillion years the universe may have, we cannot say for certain, but the physics permits it, produced life, intelligence, civilizations. Perhaps not just on one world around one star in one era, but on countless worlds around countless red dwarfs over spans of time so vast that the entire history of human civilization is a rounding error. The age of stars was also potentially the age of everything that could call itself alive. When the last star goes out, that potential ends. Not abruptly, not with a declaration, but the infrastructure for stellar-powered life, for organisms that rely on the energy gradients created by a nearby nuclear fire, ceases to exist. What comes next is another story, a much longer, much darker, much stranger story. The era of stellar remnants, the era of black holes, the deep future that makes even the trillion-year twilight seem bright and warm by comparison. The last star is out, the fusion has stopped. The final photon of nuclear origin has been travelling through the void for 1,000,000 years now, carrying the last energy the universe will ever produce through stellar fire. Behind it, the cooling white dwarf remnant of the last red dwarf drifts through a galaxy that is no longer a galaxy in any meaningful, luminous sense, just a gravitational system, a collection of dark objects held together by the same force that shaped everything, moving through space that has been expanding for longer than stars existed. The universe is dark, not the darkness of night, where you only need to wait for dawn. Not the darkness between galaxies, where you only need to look in the right direction to find a brighter patch of sky. Not the darkness of deep space, where the faint background glow of distant stellar populations still reaches you across the void. This is a new kind of darkness, a structural darkness, a darkness that is not the absence of a light that will return, but the absence of any mechanism by which light of this kind will ever be produced again. The stelliferous era is over, and the universe still has an almost incomprehensible amount of time ahead of it. Let's establish something important before we go further. The death of the last star is not the death of the universe, not even close. The universe after the last star is not empty. It is populated by an enormous number of objects, dark, cold, inert by the standards of the stelliferous era, but real, massive, present. White dwarfs in the billions of billions cooling toward their eventual black dwarf state, but still warm enough to emit faint infrared radiation for an almost inconceivable span of time ahead. Neutron stars spinning slowly through the dark, pulsing with the last of their rotational energy. Planets, rocky, icy, frozen, stripped of atmospheres but still orbiting their stellar remnants in the dark. And black holes of every size. From the stellar mass variety formed from the deaths of individual massive stars to the supermassive behemoths at the centers of dead galaxies. These objects will persist for timescales that make the entire stelliferous era, all 100 trillion years of it, look like a brief opening act. The universe, after the stars, is not ending. It is entering a new phase. A phase governed not by nuclear fusion but by gravity, thermodynamics, and the slow, patient processes of quantum mechanics operating over timescales that have no analogue in anything we've discussed so far. This is the era that comes after our countdown, but understanding it is essential to understanding what the death of the last star actually means, because without knowing what follows, you cannot fully appreciate what has been lost. The era immediately following the death of the last star is called the degenerate era. It begins at approximately 10 to the power of 14 to 10 to the power of 15 years, roughly a quadrillion years from now, and it will last until approximately 10 to the 37th to 10 to the 40th years. The numbers involved are so large that they require a different notation system than the one we've been using. A quadrillion is a 1 followed by 15 zeros. The end of the degenerate era is a 1 followed by between 37 and 40 zeros. These numbers are not just large, they are categorically, qualitatively larger than anything in our countdown so far in a way that ordinary comparison fails to convey. The entire span from the Big Bang to the death of the last star, all 100 trillion years, is a 1 followed by 14 zeros. The degenerate era extends to a 1 followed by 40 zeros. And the degenerate era is, at its outer range, roughly a trillion times longer than the entire age of stars. In this era, the dominant objects are the degenerate remnants of stellar evolution: white dwarfs, neutron stars, and brown dwarfs. These objects do not fuse, they do not generate energy in the nuclear sense, but they are not without interest, they are not without events. The white dwarfs are the most numerous objects in the degenerate era, and their story is a study in extreme patience. When we last checked on them, during the trillion-year twilight, the oldest white dwarfs were cooling toward temperatures of a few thousand degrees. The Sun's white dwarf remnant, formed roughly 10 trillion years earlier, will have cooled to approximately 2,000 degrees. The absolute oldest white dwarfs in the universe, those formed in the earliest episodes of star formation more than 12 trillion years before, will be approaching temperatures where their thermal radiation peaks in the infrared, invisible to human eyes but still detectable in principle. The cooling process never stops, it just slows. A white dwarf loses heat to its environment at a rate proportional to the temperature difference between itself and its surroundings, and as the temperature of the universe itself drops, that difference shrinks, and the cooling slows further. The asymptotic approach toward thermal equilibrium takes, depending on the physics of the white dwarf interior and the temperature of the cosmic environment, somewhere between 10 to the power of 15 and 10 to the power of 17 years. The universe itself cools as it expands. Are the cosmic microwave background radiation, the remnant thermal glow from the Big Bang, which today has a temperature of about 2.7 degrees Kelvin, drops to lower and lower temperatures as the universe expands. By the end of the degenerate era, the background temperature of the universe will be so close to absolute zero that it is essentially indistinguishable from it by any practical measure. The white dwarfs cool toward this temperature. The slowest, most gradual cooling curve in the history of the cosmos, trillions of years of almost imperceptible temperature loss, degree by degree, fraction of a degree by fraction of a degree, until the difference between the white dwarf and the surrounding space is unmeasurable. When a white dwarf finally reaches thermal equilibrium with the universe, when it is as cold as its environment, it becomes a black dwarf. And the first true black dwarfs will not form until approximately 10 to the power of 15 years from now. long after the last star has died. A black dwarf is the most inert physical object in the universe. It is not fusing anything. It is not emitting meaningful radiation. It is a dense sphere of crystallized or liquid degenerate matter, mostly carbon and oxygen for the remnants of sun-like stars, helium for the remnants of red dwarfs, sitting at near absolute zero temperature, orbiting nothing in particular in the dark. It will be there for an almost unimaginable length of time. But the degenerate era is not without events. Even in this dark, cold era, things happen, strange, slow, exotic things, but things nonetheless. The first class of events involves the physics of protons. According to some extensions of the standard model of particle physics, and this is theoretical, not confirmed, protons are not stable forever. They decay. The estimated half-life of a proton under certain theoretical frameworks is approximately 10 to the 31st to 10 to the 36th years. If proton decay is real, if protons do eventually decay into lighter particles and radiation, then all the matter in the white dwarfs, black dwarfs, neutron stars, and planets of the post-stellar universe will gradually dissolve. Not quickly, not dramatically, but over time scales of 10 to the 31st to 10 to the 40th years, every atom of ordinary matter will spontaneously disintegrate. The energy released by proton decay is minuscule. Each individual decay event produces a tiny amount of energy, a small flash of radiation. But across a white dwarf containing perhaps 10 to the power of 57 protons, these decays add up. A white dwarf undergoing proton decay glows faintly, not from nuclear fusion, not from residual thermal energy, but from the slow disintegration of its own matter, a ghostly, negligible luminosity, an echo of stellar fire in an era long after stellar fire has ended. If proton decay occurs at the rates some theories predict, then by approximately 10 to the 37th to 10 to the 40th years, all the ordinary matter in the universe, every white dwarf, every neutron star, every planet, every rock, every atom that was ever part of a star or a world or a living organism will have decayed. What remains is radiation and leptons, electrons and positrons drifting through a universe that has been stripped of its matter. This is the end of the degenerate era. The matter era is over. If proton decay does not occur, if protons are truly stable as the standard model itself predicts, then the degenerate era continues even longer, and the white dwarfs and neutron stars persist indefinitely, growing colder and colder, but never quite decaying. The subsequent eras we'll discuss still occur, driven by other processes, but the matter takes longer to disappear. After the degenerate era, however it ends, comes the black hole era. This is the period when black holes are the dominant objects in the universe. Everything else, if proton decay has occurred, is radiation and leptons. The black holes are the only significant concentrations of mass energy remaining. The black hole era spans from approximately 10 to the power of 40 years to 10 to the power of 100 years. That upper bound, 10 to the power of 100 a googol, is the approximate timescale for the evaporation of the largest supermassive black holes via Hawking radiation. The black hole era is named for its dominant objects, but it is also, in a strange way, a luminous era. Not with the warm, intense light of stars, but with Hawking radiation, the faint thermal glow emitted by black holes as a consequence of quantum effects at the event horizon. Every black hole emits Hawking radiation. The emission is extraordinarily faint. For large black holes, a stellar mass black hole emits Hawking radiation at a temperature so close to absolute zero that it is unmeasurable against any realistic background. But it is real, and it adds up to something. Not warmth, not anything that could sustain a temperature gradient useful for life, but something. A universe that is not entirely at thermal equilibrium. A universe that still has faint energy differentials. Black holes slightly warmer than their surroundings, emitting their ghost light into the cold. Over the course of the black hole era, black holes evaporate. The smallest ones first, stellar mass black holes, those of 10 solar masses, evaporate in approximately 10 to the power of 67 years. Intermediate black holes of millions of solar masses take longer. The supermassive black holes, the monsters at the centers of galaxies, those of billions of solar masses, take approximately 10 to the power of 83 to 10 to the power of 100 years. When the last supermassive black hole evaporates, somewhere around 10 to the power of 100 years, the black hole era ends. The last significant concentration of mass energy in the universe disintegrates in a final burst of Hawking radiation. A brief, brilliant flash, brief only relative to the era it ends, which is to say it occurs over millions of years, but is the most energetic event in the universe in the entire epoch, and then gone. The black hole era is over. After the black hole era comes what cosmologists call the dark era. This begins at approximately 10 to the power of 100 years and extends, as far as current physics can project, forever. The dark era is the universe in its final state. All the matter is gone, decayed if proton decay occurs, or locked in the evaporated remnants of black holes if it doesn't. The universe contains only radiation. Photons at extraordinarily long wavelengths is stretched by the expansion of the universe until they carry almost no energy at all, and the lightest particles, electrons, positrons, neutrinos. These particles drift through an expanding universe separated by distances so vast that interactions between them are effectively impossible. The universe is, at this point, as close to absolute thermal equilibrium as physics can achieve. There are no more energy gradients, no more temperature differences, no more processes that can extract useful work from the environment. This is what thermodynamics calls heat death. Not the death of heat in the sense of cold exactly, but the equalization of all temperatures, the elimination of all gradients, the end of any process that requires a difference between one region and another to drive it. Heat death, the final state. At the asymptotic end point that the universe has been approaching since the moment of the Big Bang, through every stellar fire, every supernova, every cooling white dwarf, every evaporating black hole. The death of the last star was a milestone on this road, an important one, the end of the era in which nuclear energy sustained the universe's brightest and most energetic features. But it was not the end of the road. The road continues through the dark and the cold for a time so vast that the 100 trillion years of stellar life is, by comparison, genuinely brief. Let's bring this back to where we started. We began this video with a star burning tonight somewhere in the sky that has been burning for longer than the Earth has existed. We noted that it will one day go out, not with drama, but with patience, and with the slow exhaustion of its last fuel reserves. We asked the question, when does the last one go out? And we've walked through the answer, step by step, phase by phase. From our present moment, where the universe is young and bright and busy, through the first great dimming of the sun-like stars, through the trillion-year twilight of the red dwarf era, through the final countdown of the smallest stellar fires, to the moment the last fusion reaction occurs in the last stellar core in the observable universe, approximately 10 to 12 trillion years from now. Give or take the uncertainties in our models of the smallest red dwarf physics. But here is what I want to leave you with, not the number. The number, by this point, you know. What I want to leave you with is the implication of everything we've walked through. Télécall. Because the death of the last star is not just a physics fact. It is a statement about the nature of the universe we inhabit and about our place within it. We are extraordinarily early. This is the first and most fundamental implication of everything we've discussed. If the stelliferous era lasts 100 trillion years and we are 13.8 billion years into it, then we are at the 0.014% mark. Not the beginning. The universe had its actual beginning, its most energetic and eventful early phases, long before Earth formed. But early. Staggeringly early. If you compressed the stelliferous era into a calendar year, we are at approximately 5 a.m. on January 1st. The universe has not had its long afternoon yet, not even close. The trillion-year twilight of the red dwarf era, that vast, dim, or patient epoch that we described in Part 3, hasn't even begun. The stars that will burn longest, the red dwarfs that define the back half of the stelliferous era, are still in their infancies. TRAPPIST-1 is less than 8 billion years old. It has 12 trillion years ahead of it. It has barely started. We arrived early, implausibly early. On the cosmic timescale, we evolved around a star, the Sun, that burns fast by red dwarf standards. A star that will be dead and cold before the stelliferous era is even 1/10 of the way through. By accident of physics and chemistry and the particular conditions of our solar system's formation, we are observers in the bright, energetic, brief opening chapter of a story that is mostly still ahead. This should give you pause. It should make you wonder. TT. As the cosmologist Fred Adams and others have wondered, whether our position at the beginning of the age of stars is a coincidence or something more meaningful. Whether the conditions that allow life like ours, carbon-based, dependent on a sun-like star, requiring liquid water and clement temperatures, are specifically a feature of the early stelliferous era. Whether life of a different kind, life adapted to the dim, patient warmth of red dwarfs, life on different timescales with different biochemistry, different timescales of evolution and civilization, might be far more common in the long middle of the age of stars than life like ours is now. We don't know, but the question itself is extraordinary, and it is a question that only the countdown makes visible. The countdown also forces a reckoning with time itself. Human beings are extraordinarily bad at intuiting large numbers. We evolved in an environment where the relevant timescales were seasons, lifetimes, generations, at most a few thousand years of oral and written history. We have no instinct for millions of years. We have no emotional response calibrated to billions. The 12 trillion years between now and the death of the last star is simply beyond the reach of intuition. But the countdown gives us a framework. It breaks the incomprehensible into phases. Each phase has a character, a quality, a dominant feature. The phase of massive star deaths, brief and violent. The phase of sun-like star deaths measured in billions, the phase of red dwarf dominance measured in trillions, the phase of the final dwarfs, the last burning embers at the bottom of the stellar mass range. And walking through those phases, as we've done in this video, gives you something that the raw number doesn't: a sense of trajectory, of where the universe is going and how it's going to get there, of what is being lost at each stage and what persists, and for how long. The universe is moving toward darkness, slowly, over a span of time that makes the current age of the cosmos look like a single afternoon, but unmistakably, irreversibly, in the direction of cold and dark and quiet. The stars are temporary, all of them, everyone, the ones burning tonight, the ones already dead, the ones not yet born. Every stellar fire that has ever burned or will ever burn in the history of the observable universe is a temporary phenomenon, a brief interruption in the cold, a local, transient, a beautiful deviation from the universe's default state of equilibrium. And within that temporary phenomenon, within the 100 trillion years of stellar fire, there may be something even more temporary: life, awareness, the capacity of the universe to understand itself. The brief, improbable, extraordinary phenomenon of minds arising from matter and looking up at the sky and asking the question we've been trying to answer in this video: how long until the last star burns out? The answer is longer than you can imagine and shorter than the universe has to live. 12 trillion years is the answer in round numbers, a number so large it defeats intuition. But measured against the universe's full timeline, the dark era, the heat death, the eternal and lightless afterward, 12 trillion years is a thin, bright strip, a narrow band of warmth and light in a story that is mostly cold and dark. We are inside that strip, right now, tonight. The stars are burning around us, the nearby ones visible to the naked eye, the distant ones accessible only to our telescopes, the red dwarfs nearby and invisible but present. The nuclear fires are going. The light is on. It will not always be on. Not in 12 trillion years, not in 12 billion, not in 12 million, not in 12,000, but eventually, after a span of time so enormous that it comprehends every era of human history 1 trillion times over, the last fire will go out. The last proton will fuse. The last photon of nuclear origin will emerge from a stellar core and begin its journey through the dark. And the stelliferous era will end. There's one final thought I want to leave you with before this video ends. When you lie in the dark tonight, listening to the universe breathe, or rather listening to the absence of breath, the silence that fills the space between thoughts, consider this: every atom in your body was forged in a star, the carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron at the center of your hemoglobin, carrying oxygen from your lungs to every tissue in your body with every heartbeat. Every one of those atoms was assembled from lighter elements in the nuclear furnace of a star that died before the sun was born. A star that burned its fuel over millions or billions of years, fused hydrogen into helium, into carbon and oxygen and nitrogen and iron, and then, at the end of its life, expelled those atoms into the interstellar medium in a supernova or a planetary nebula or a stellar wind. Those atoms drifted through the galaxy for billions of years. They were incorporated into molecular clouds. They collapsed with other atoms into new stars and new planetary systems. They were present in the solar nebula that condensed into our sun and our planets 4.6 billion years ago. They were present in the oceans of the early Earth. They were present in the first living cells that arose from those oceans roughly 3.8 billion years ago. They have been cycling through life on Earth ever since, through every organism that has ever lived, through the atmosphere and the ocean and the soil, and back into organisms again, over and over, for nearly 4 billion years. And tonight, they are in you. You are made of star stuff, not metaphorically, literally. The atoms that constitute your body were created in stellar cores that burned billions of years before the Earth existed. You are the product of the stelliferous era, assembled from the raw material that the universe's nuclear fires produced over billions of years of star birth and star death. When the last star goes out 12 trillion years from now, the age that made you, the age that made everything you are made of, will be over. The era of nuclear fire, of hydrogen fusing into heavier elements, of stellar winds and supernovae seeding the interstellar medium with the ingredients for planets and oceans and life. That era will be done. It will have lasted 100 trillion years. It will have produced, among other things, you. And in the long, cold dark that follows, and the quadrillions and quintillions of years of the degenerate era, and the unimaginable vastness of the black hole era, and the eternal equilibrium of the dark era, the atoms that were you, if they haven't decayed, will drift through a universe that no longer makes things like you. A universe that has finished its brief, brilliant, productive period of stellar fire, and has settled into a silence longer than stars. But you were here during the fire. You came to consciousness during the few billion years when the universe was young and bright and warm enough to permit the extraordinary accident of life. You were present in the age of stars. That is not a small thing. The universe burned for you, for everything, for 100 trillion years. The least we can do is look up and notice. In the countdown to the last star, right now 200 sextillion stars burning across the observable universe. Our sun, in its middle age. The age of stars just beginning its long afternoon. 5 billion years. Our sun leaves the main sequence. Earth becomes uninhabitable. The first cohort of sun-like stars begins to die. 10 billion years. Most sun-like stars have become white dwarfs. The Milky Way and Andromeda have merged into Milkomeda. The galaxy glows dimly in red. 1 trillion years. The largest red dwarfs begin to die. The universe enters the trillion-year twilight. New star formation has essentially ceased. 5 trillion years. The mid-sized red dwarfs are dying. The galaxy is dominated by stellar remnants. The remaining fires are small, dim, and ancient. 10 trillion years. Only the smallest red dwarfs remain. The universe is entering the final phase of the stelliferous era. 12 trillion years. The last red dwarf exhausts its hydrogen. It cools, contracts, fades. The last fusion reaction occurs. The last photon of nuclear origin begins its journey into the dark. The stelliferous era ends, the age of stars is over, and the universe, patient, cold, vast, and dark, keeps going. If this video made you think, made you feel the weight of cosmic time, made you lie a little longer in the dark thinking about what it means to be alive during the age of stars, then it did what it was supposed to do. We'll be back with another countdown, another timeline, another deadline baked into the structure of the cosmos. The universe is full of clocks. We just have to know where to look.